All right, let's dive in. Today, we're not just going to be doing math. Nope, we're going to learn an entirely new language. A language that describes the very fabric of the world around us, from a honeycomb all the way to a skyscraper. We're going to learn how to speak the language of space itself.
I mean, just think about that for a second. Instead of just seeing shapes, what if you could understand and describe their relationships with perfect clarity and logic? That's the real power of geometry. It's this universal language for describing how everything is put together, from a tiny molecule to an entire galaxy.
And just like any language, you got to start with the basics, right? So first, we'll learn its alphabet, the fundamental building blocks. Then we'll combine those letters to form some simple words, like segments and angles. After that, we'll get into the grammar, the rules of logic that really make this language work. And finally, we'll put the whole shebang together to tell a complete geometric story.
So every language starts with its letters, and in geometry, our alphabet is made of just 3 core ideas. They're actually called undefined terms, which sounds weird, but it's just because they're so fundamental, we just have to accept them as our starting point. Everything else is built on these.
First up, we have the point. It's literally just a location. Think of the tiniest dot you can make, and then imagine it has no size at all. Yeah, no length, no width, no height. It just says, I'm right here. It's the letter A of our new language.
Now, what happens if you string an infinite number of these points together in a perfectly straight path? Well, you get a line. A line has only one dimension, length. But here's the crazy part. It has no end. It just goes on forever and ever in both directions. It's kind of like the concept of infinity made visible. Okay, so if a line is an infinite string of points, a plane is like an infinite sheet of them. Imagine a perfectly flat piece of paper that just extends forever in all directions. It's got length and width, but absolutely zero thickness. This is the stage where most of our geometric stories are going to take place.
And check this out. This is how our alphabet starts to come together. You can see 2 planes, M and N, just slicing right through each other. And there's a line L piercing both of them. See those points C, D, E, and F? They're called collinear, which is just a fancy way of saying they all sit on the exact same line. See? Even with just these 3 basic letters, we can start to build a pretty complex little universe. All right, now that we have our letters, points, lines, and planes, we can start forming some simple words. These are the concepts we'll use to actually measure and describe the space all around us. So, a line goes on forever, which is a really cool idea, but not super practical if you want to measure something, right? So for that, we create a line segment. It's just a piece of a line that has 2 clear endpoints. It has a definite, measurable length. Then you have a ray, which is kind of a hybrid. It's got one endpoint, a starting point, and then it shoots off infinitely in just one direction, like a beam from a flashlight. Now, once we have a segment, we can actually measure it, and that brings us to a super important concept, distance. It's simply how far apart 2 points are. And here's a key rule in geometry you can't ever forget. Distance is always a positive number. There's no such thing as negative space between 2 spots. So how do we actually calculate distance on, say, a 2-dimensional plane? Well, if you look here, you can see we can just form a right triangle using the horizontal and vertical distances between 2 points. And the distance between them? It's just the hypotenuse. This means that famous, kind of scary-looking distance formula, it's really just the good old Pythagorean theorem dressed up for a coordinate plane. The next word in our vocabulary is the angle. This is what happens when 2 rays share a common endpoint, which we call the vertex. Angles are how we measure turns, how we describe corners, and how we understand the relationship when lines intersect. They are absolutely essential for describing shapes. Okay, so we've got our alphabet and some basic words. But, a language is pretty useless without grammar. You need a set of rules that lets you combine words into statements that actually make sense and are true. In geometry, our grammar is logic. So there are 2 main ways to reason about things. Inductive reasoning is all about spotting patterns. You see a few examples and you make an educated guess, a hypothesis. But deductive reasoning is totally different. It starts with things we already know are facts and uses pure logic to reach a conclusion that must be true. And geometry, it's all about the certainty of deductive reasoning. Now, to build these rock-solid deductive arguments, we need rules. Just think of them like the rules of grammar in English. You can't just throw words together in any old order. In geometry, our foundational rules are the properties of equality, which you probably remember from algebra.
And you can see on this slide just how simple and, well, logical these rules are. The addition property, for example, just says that if two things are equal, you can add the exact same value to both sides and they'll stay equal. Makes sense, right? Or the substitution property, which just means if A equals B, you can swap them out for each other anywhere you want. These are the tools we use, step by step, to build a completely unbreakable argument. And now we're ready. We have our letters, our words, and our rules of grammar. We can finally combine them to tell a complete logical story that proves something is undeniably true. In geometry, we call this story a proof. So here's the plot for our first story. We're given this triangle, JHK. The one and only fact we know for sure is that angle H and angle K are not equal. Our mission, should we choose to accept it, is to prove, using our geometric language, that this triangle cannot possibly be an isosceles triangle with base HK. We're going to tell this story using a powerful little technique called proof by contradiction. First, we assume the exact opposite of what we want to prove. So let's just pretend for a minute that the triangle is isosceles. Okay, if it's isosceles, then by the very definition, sides JH and JK have to be equal. But here's the kicker. There's a core rule, a theorem, that says if two sides of a triangle are equal, then the angles opposite them must also be equal. That means angle H would have to equal angle K. But wait a minute, that's a contradiction. The one thing we were told at the start was that angles H and K are not equal. Since our assumption led us to a logical impossibility, the assumption itself has to be false. The triangle cannot be isosceles. And there you have it. We used our alphabet of points and lines, our vocabulary of angles and sides, and our grammar of pure logic to construct a story. A story that didn't just suggest something, it proved it with absolute, undeniable certainty. That right there is the power of speaking the language of geometry.
So let's end on this thought. We just used a clear, logical process to build an undeniable truth about a simple little shape. But this same method, starting with facts, using clear rules, building a step-by-step argument, that can be applied to so much more than just triangles. So the real question is, what truths can it help you build?